All right. Hi, everybody. How are you? So we are going to now set the stage for our next method of integrating. Okay. The next method of integrating is called integrating by decomposing a rational expression into partial fractions. Okay. Before we can learn that integration method, however, you have to first understand what it means to decompose a rational expression. All right. So let's begin. So here I'm starting with a rational expression. And when we decompose it, decomposing and I look what I did here, I just called it a fraction because essentially a rational expression is a fraction of sorts, a fraction of functions of x perhaps. When you decompose a fraction, what that means is breaking up the fraction and expressing it as a sum of two or more simpler fractions. And we're going to talk about what simpler fractions means in a second here. So let's just kind of get through the exercise of decomposing. So here's the original rational expression. And the first thing I did here was I rewrote the rational expression with the denominator as a set of factors. Okay? Now I'm going to go over here to the side for a second and just kind of use our old friend here, a regular fraction, okay? If I have the fraction 5/12, and I know that I can rewrite 12 as 4 times 3 or 6 times 2, I'm just going to choose 4 times 3. The point here is that this fraction, 5/12, could conceivably be the sum of a fraction that has a denominator of 4 and the sum of a fraction whose denominator is 3. Okay. Now I know some of you are saying, well, this 4 I can write as 2 times 2, and I know that you can, but I just want to disregard that for right now. The point I'm making is that a fraction, in this case 5/12 right here, I could rewrite it as a sum of two simpler fractions. And by simpler fractions, you probably see what I mean by simpler. The denominators are they are closer to being prime, if not prime itself, right? So if I were to go even further, I could say, perhaps 4, which we know is 2 times 2, I could express 5/12 as a sum of fractions where the denominators are 2, 4, and 3. Okay, so the idea of taking a fraction and expressing it as a sum of two or more simpler fractions comes in very handy in the case of integrating. I guess the first thing I want you to notice here is that, because you see where we're going, if I had to, for example, integrate, take the antiderivative of 3 over x squared minus 2x minus 3 dx, and some of you may say, well, let's just pull the 3 out. Okay, many of you would stop right here and notice that if I were to be given the task of integrating this rational expression, none of the integration methods learned so far, that includes parts, u sub, and straight antiderivative rules in reverse, none of those methods help us. Okay, so where we're getting to is how do you deal with rational expressions that require antidifferentiating? Okay, let's go back here. So the task at hand in front of us is if we have this fraction, 3 over x minus 3 times x plus 1, let's express this fraction, in quotes, as a sum of fractions whose denominators may be this, right? We don't know what a and b are, but we do know, just like in the example over here of 5/12, I could express 5/12 as a fraction, as a sum of fractions, one whose denominator is 4, one whose denominator is 3. The same thing is going on here, right? And here's the thing, here's where I want you to see something. If we can somehow figure out what a and b are, and if we find that a and b are in fact constants, if I'm tasked with, if the original task was integrating this, and I cannot, well, maybe it'd be easier to integrate the version on the right-hand side, right? Because if I integrate the right-hand side, I can think of this as an integral of a over x minus 3 dx plus the integral of b over x plus 1 dx. And of course here, if a and b are in fact constants, hopefully you all see that a simple u sub gets the job done very well. But again, we keep getting off track. So here's what I'm going to do. I'm going to go over here and say, okay, 3 over x minus 3 times x plus 1 is equal to a over x minus 3 plus b over x plus 1. We need to now solve for a and b. Here's what we're going to do. We're going to multiply both sides of this equation right here by the common denominator. We're going to multiply both sides of the equation by this expression right here. When you do that, we get this. 3 equals a times x plus 1 plus b times x minus 3. Okay? Now what's really slick and dirty and tricky and slick and like slick, like kind of very backhanded is, if you look at this equation right here, there is no domain restriction on what x can be. And in fact, I'm solving for a and b, right? X can be anything. So what I'm going to do is let x equal values that are going to be very convenient for me. And I notice that if I just let x equals -1, if I let x equals -1, I'm going to plug in -1 for x. I get 3 equals 0 plus b times -4, or b equals -3/4. So I have just found b. I'm now going to choose let x equal 3. Okay, if I let x equals 3, my equation in pink up there becomes 3 equals a times 4 plus 0, or a equals 3/4. If you're wondering, will a and b always be opposite of each other, the answer is no. Okay, now what I've just done is I have rewritten my original rational expression, which was 3 over x minus 3 times x plus 1, as the sum of, let's see, 1 over 2 simpler fractions, so to speak. Okay, look, I could have written this as 3/4 over x minus 3, but you're going to see what I'm going to do here in a minute. And now I can do this. Since the task probably is going to be integrating this at some point, I am now going to integrate the right-hand side instead, because the right-hand side is integrable very easily. A simple u sub here, if I let u equals x minus 3, I'm going to get 3/4, the natural log of the absolute value of x minus 3, minus 3/4 natural log of x plus 1. And then, of course, plus c. Okay, so this method of integrating, it's called integration by partial fractions, right? Partial fractions is right here. The partial fractions, where am I? Goodness gracious. The partial fractions of 3 over x minus 3 times x plus 1 are right here. Here are the partial fractions. So when do you use integration by partial fractions? Well, you use them when we have a rational expression, okay? When I see you next week, we're going to continue talking about different kinds of rational expressions. But right now, the rational expressions that we're going to decompose are going to be proper rational expressions where the numerator is a constant. Okay, that's going to be the focus of this screencast. So those are the easiest kinds. A proper rational function is one where the degree of the denominator is greater than the degree of the numerator. Okay, so that's a proper rational expression. And I said that the first time through here, we're going to have only constants in the numerator. Okay, so with that, let's go ahead and try an example. Why don't you try and evaluate this? Oh, no, don't want to do word. Okay, evaluate the indefinite integral of -2 all over x squared minus 9 dx. Okay, and why don't you go try it on your own and then replay me for the result or work with me, either way. All right, I mean, I, as you know, have the tendency to kind of do this, which is all well and good, but in this case, if you want to pull the constant -2 out, just like up here, you could have pulled the constant 3 out, certainly. If you pull the constant out, just make sure you don't lose it in your work, okay? So now what I'm going to do here, I'm going to do this one in a slightly different way than I did the top question. I'm just going to decompose that guy, all right? So the first thing I'm going to do is recognize that 1 over x squared minus 9 could be written as 1 over x plus 3 times x minus 3. This is equal to some number over x minus 3 plus some number over x plus 3. Multiplying by the LCD right here on both sides of the equation gives us 1 equals a times x plus 3 plus b times x minus 3. Okay, I'm going to conveniently choose my values of x to solve for a and b. If I let x equals -3, I will get b equals -1/6. If I let x equal +3, I get a equals 1/6. So then at the end of the day here, I have, okay, I'm going to go back and make sure I don't lose anything. This becomes -2 times the antiderivative of, you know what, I'm going to do this, times the antiderivative of 1/6 times 1 over x minus 3 dx minus 1/6 times the antiderivative of 1 over x plus 3 dx. Okay, and I'm going to be very careful. I'm not going to lose anything here. This becomes -2 times 1/6 times the natural log of the absolute value of x minus 3 minus 1/6 times the natural log of the absolute value of x plus 3, okay? And maybe you'll take the -2 and distribute. We get -1/3 natural log of x minus 3 plus 1/3 the natural log of the absolute value of x plus 3. And if you were feeling particularly inspired, maybe you'll even do this. This becomes the natural log of the absolute value of x minus 3, where all of this is raised to the -1/3. That's the argument of the log. This is just property of logs, boys and girls. Natural log of the absolute value of x plus 3 to the 1/3, okay? All right, and then you can even use a property of log, again, to combine this into one log expression if you want to, but that's up to you, all right? So in this screencast, just to recap, we are talking about how we decompose rational expressions, and we are working through the easiest case, the easiest version of integration by the method of partial fractions. All right, have a good week.